But today we're joined by Rus Belikov, who's going to talk to us about imaging exoplanets. Rus is a graduate of Stanford, and he spent some time on the East Coast before he moved back here during the dot-com boom, was seduced into optics and electronics in the dot-com boom, but decided to get on board with the exoplanet craze in science, and now he's going to talk to us about his work at NASA Ames on developing technologies for direct imaging of exoplanets. So if you'll join me in welcoming Rus.
All right, well, thanks for coming here, and with the new location and everything, sorry about the delays. As Adrian mentioned, my talk is about direct imaging of Earth-like planets. And I view this as the next step after Kepler, or at least I'm hoping this would be the next step after Kepler. There have been a few Kepler talks at this series, so this is kind of a natural progression, I think. So my talk consists of 3 parts: the past and present of exoplanets, then how we can image another Earth. Sorry, I guess we need to turn down the microphone a little bit.
You might have to turn it down on your...
I see. Gain.
Yeah, right there. Or you could perhaps move it away from you. Just test it a few words.
All right, let's try this again. How about this? Is this better? Yeah, I thought this was a little bit too loud. Okay, so 3 parts. Past and present of exoplanets, how we can image another Earth, which is the work that I do at Ames, and future. Also, since there's a range of experiences here, I tried to keep my talk a little bit on a less technical level, so hopefully this isn't going to offend the technical people in the audience. Okay, so moving right along. The question that I'm most interested in is whether there's another Earth out there. So this is clearly a profound question that we can ever ask us, or one of the most profound questions that we can ask as human beings, and it's a very exciting question. And the cool thing is that we can actually answer this question with Kepler and follow-up missions. We're right on the verge of answering this question in the next few years, and then characterizing these planets in the following decades. So. This question is a very old question, and in particular, as early as 300 BC, a guy named Epicurious from ancient Greece was saying that there are infinite worlds both like and unlike this world of ours, and that we must believe that in all worlds there are living creatures and planets and other things we see in this world. So this is quite remarkable that people have thought about this 2,000 years ago. A little bit closer to the present times, in the Middle Ages, Jordana Bruno wrote that there are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. And we see only the suns because they're the largest bodies and they're luminous, but their planets remain invisible to us because they're smaller and non-luminous. But the countless worlds in the universe are no worse and no less inhabited than our Earth. So, and this was written during a time that people thought the Earth was the center of the universe, and poor Jordana Bruno was burnt at the stake for his beliefs. I hope I get a better reception from you guys. I think this is okay given that this is a SETI audience. So. And then, of course, there's Galileo, who was arguably the very first person to dethrone Earth as being the center of the universe by showing that there are planets that are manifestly orbiting an object other than the Earth, namely the Jovian satellites. And you can see some of his very first notes on these observations. You see the big circle there is Jupiter with Jovian satellites orbiting around it. So Galileo arguably ushered the so-called Keplerian revolution that dethroned Earth as being the center of the universe, and then we had a series of other Keplerian revolutions. Not only is Earth not the center of the universe, but the sun is not the center of the galaxy is not the center of the universe. Even the matter that we're made of is not the dominant matter of the universe. But there's still one anthropocentric notion that we cling to, and that notion is that Earth is the center of life. And that is one thing that we could debunk, hopefully, by showing that there's another Earth out there, and maybe there's life on that other Earth. It's interesting that there was no hard evidence for planets orbiting other stars until 1995. There have been a few objects found around stars. There was an object found around Pulsar in '92, but generally 1995 is considered to be the year when the very first extrasolar planet was found. By the way, maybe we could dim these lights a little bit. It seems like, can you guys see things okay, or is it, yeah. So is there any way we can dim the lights? Is Adrian around? Okay. Okay, well, in interest of time, I'm gonna go on, but maybe if Sophie can ask Adrian, that'd be great. All right. So now to date, for the past 15 years, since '95, 473 planets have been found, and they orbit around 402 stars. So some of the stars we know have multiple planets. And there are 4 methods that are used to detect these planets. Actually a little bit more than 4, but the main one is the so-called wobble method, or radial velocity. And the way that works is basically the star and the planet, the planet doesn't really orbit a star, they both orbit their common center of mass, so the planet induces a wobble in the star, and you can detect that wobble either by looking at the spectrum of the star as it moves towards and away from you. It gets red shifted and blue shifted. Or you can use the wobble method number 2, which is called astrometry, which actually looks at the changes of the location of the star and how the location of the star changes. Now, most of the planets, the majority of the planets, if you exclude Kepler for now, have been found by the radial velocity method. So there's also the transit method, which basically works by having a planet pass in front of the star, and as the planet passes in front of the star dims a little bit, and by looking at these periodic dimmings, you can see, you can infer the presence of a planet. And that's how Kepler works. The gravitational microlensing method is also very interesting, although it hasn't been as prolific. And the way that works is if you imagine 2 stars being in your line of sight, and you're looking at this middle star, as this middle star passes in front, or if it happens to pass exactly in front of your background star, then any planets around that star will modify the light from the background star by bending them with gravitational microlensing. And by looking at the shapes of how the brightness of the star changes because light is being focused essentially by gravitational microlensing, you can then infer presence of planets, and you can figure out their masses and so on. So I had a couple of movies here demonstrating this, but I don't think they're going to work because we're using a different laptop. Sorry about that. But speaking of transits, I couldn't resist putting this slide in. We can see transits in our own solar system. We have 2 planets that are inward of Earth to the Sun, so we can see them transit the Sun. And these planets are Venus and Mercury. Venus in particular will have a transit in 2012 on June 5 through 6, depending on where you are. And so you can see this if you look with a safe filter at the Sun. You can see Venus passing across the Sun, and you better catch it 2012 because the next one after that is 2117. I'm not sure if any of us will be alive then. So okay, Now, what I'd like to show by this graph is that most of the 473 planets that have been found are size of Jupiter or Saturn. They're big gas giant planets. And if we're looking for life, what we really want to look for is small planets such as Earth and Mars. You can probably just barely see them here with all the lights, unfortunately. So, oh, great. Still not quite as dark as I would like, but a little bit better. So these 4 planets of our solar system are shown to scale. You can see how much smaller the Earth is than the Jovian planets. And the graph there shows the planets found as a function of year. So this is publication date. And the y-axis is a logarithmic scale showing the mass of those planets in units of Jupiter mass. So you can see on our own solar system here is Jupiter, Saturn, Neptune, and Earth is all the way down here, about 300 times less massive than Jupiter. That's off the scale. So most of the planets are really big gas giant planets, which, as far as we know, are not habitable or cannot support life as we know it. However, if you look at the trend of the minimum mass planet, it's remarkably how linear it is. And in 2009, there was a planet whose mass, actually minimum mass, was about 2 Earth masses. So it's right there. And if you extrapolate this curve, we would expect to start finding actual Earth mass planets in this year and next year, which is right on schedule because Kepler should be able to provide us with those planets. Now, every week there are more and more extrasolar planets that are found, and in particular, just yesterday, the smallest exoplanet was announced to date. So this was a bit, very much of a coincidence. I launched up my computer this morning and I saw this announcement, so I had to insert this slide. It's not confirmed, but the false detection probability is only 1.4%, according to the authors at least. So it seems like it's a fairly safe bet. But in any case, the star is HD 10180. It's a Sun-like star, type G1V. And it has a lot of planets. It has as many as 7 planets. And the one that was found yesterday is, as I said, 1.4 Earth masses. Now, there's one caveat to that. These planets have been found using the radial velocity method, which doesn't actually tell you the mass, but it rather tells you the minimum mass. And the reason for that is what you're measuring is the projection of the motion of the star to your line of sight using radial velocity. So it only just, happens to give you the lower limit on the mass. However, statistically, this lower limit should be close to the actual mass of the planet, unless you're very unlucky. So, having said that, note that the orbital period note that the distance to the star is 0.02 AU, which means it's much, AU is the distance between the Earth and the Sun, which means it's much closer to its star than our Earth is. And in fact, it's the distance from the star, I believe, is comparable to the actual size of the star. So this planet is getting completely roasted. Remember, this is a Sun-like star. And you can just imagine what the star would look like if you were standing on that planet. It would fill your, almost your entire field of view, and it would just be crazy. So this is kind of what it would look like. And so obviously it's too hot to support any kind of life, but it is a small planet. So now, habitability not only requires Earth-sized planets, more or less. There's some room to play, but if you get if a planet is too large, then it retains too much of its original hydrogen atmosphere and it blows up to be a gas giant. And if a planet is too small, then it can't retain any atmosphere, and it also doesn't have probably a magnetic field because it solidifies, cools down very fast, and solidifies. So there's only a range of sizes around Earth-sized for planets that could be habitable. But there's another habitability factor, and that is, of course, the distance from the star. If a planet is too close to the star, then it gets too hot. If it's too far away from the star, then it gets too cold. So we call the zone around a star where planets can support liquid water the habitable zone. Around our sun, this habitable zone extends roughly from Venus to Mars. So Venus and Mars are roughly on the edge of being habitable. They happen to be not habitable in our solar system. So our best habitable candidate so far is this planet called Gliese 581d. It's the fourth planet orbiting the star called Gliese 581. And it is located roughly, or at least close to the habitable zone. It receives 30% of the intensity of sunlight on Earth, or 75% of sunlight on Mars. So if it has a strong greenhouse effect, it can potentially be habitable. But one problem with it is that its mass is from 7 to 14 Earth masses. So that's about the boundary of a planet size where we don't know if it's a gas giant or a Neptune-sized planet or a super-sized Earth. But so far, this is probably our best habitability candidate. Now, the first true, unambiguous Exo-Earth detection, and by Exo-Earth I mean a planet that's Earth-sized and in the habitable zone around its star. So the first unambiguous detection like that will probably come from the NASA Kepler mission. Now, the Kepler mission, as I mentioned, uses the transit method to look at hundreds of thousands of stars and trying to detect planets around them. And its sensitivity is good enough that it can detect Earth-sized planets around these stars. It was launched about a little bit more than a year ago. And recently, the data from the first quarter of observations was released. And so some of this data is plotted here. So on the top graph, what you see is the 306 of Kepler candidates from the first quarter of observations. And the x-axis is the planet radius in terms of Earth radii. So one Earth radius would be right here, and it goes up to 22 Earth radii. And this is a histogram of the number of planets based on Earth, on size of the planet. So one remarkable thing that you can see here is that there are more small planets than there are large planets. In fact, you can fit a 1 over r squared curve here, which basically means that the cumulative area on small planets is exactly the same as the cumulative area on large planets throughout the universe, or roughly that seems to be the case. It's pretty an interesting kind of fact to keep in mind. If you compare this to the previous transit detections, you can see that there were very few small planets, and the reason for that was that there was a bias in previous detections towards detecting large planets. Large planets are easier to detect, so those are the ones that were found. But Kepler is now opening up a whole new other space of planets right here, which is, and it's basically showing us that in reality, even though we didn't find any small planets before Kepler, there are many more small planets than there are large planets. So this is very exciting and very encouraging for finding another Earth, of course. But I personally consider the holy grail of detection methods to be direct imaging. And of course I'm biased here because that's what I happen to be working on. But the reason I consider direct imaging of planets the holy grail is that it allows you to take the spectrum of a planet and then figure out what's on the planet. Now there's another way you can take a spectrum of planets, and that's using transits. There's a trick of using secondary transits to extract the spectrum of planets. We had a talk at this seminar series a few weeks ago by Heather Knudsen, who spectacularly demonstrated how possible this is. However, this technique works well for large planets, but it gets harder and harder to do that for small planets. And arguably, direct detection is maybe easier to get the spectrum with direct detection on small planets rather than transits. It also depends on the type of the star somewhat. But in any case, direct detection is a very promising technique that not only would let you characterize, the size of planets and such things, but also spectrally analyze it and detect possible, oxygen and water on it. Now, here are a few images. Unfortunately, you can't see them very well, but maybe you can kind of just make out a few things here. So these images are images that were taken to date of extrasolar planets. The top row corresponds to planets that are not confirmed as planets, but the bottom three, or at least the bottom two, are confirmed planets that were detected by direct imaging around other stars. So this star, the star here has been subtracted, and you just see the noise from the star. You can see 3 planets orbiting around it. And then there's another star called Fomalhaut, which you might have seen in the sky if you know where your stars are. And can anybody actually see anything in this image there? No. Okay. Yeah, I wish there was some way to darken this. But, well, let me see if it shows up. Can anyone see anything on this image?
Yes.
Okay. So this is a blown-up image of Fomalhaut, and you may be able to see a disk around Fomalhaut here. It's a debris disk, and there's a small planet, a small image of a large planet orbiting Fomalhaut right there. Now the distance from Fomalhaut to that star is very large. I think it's something like 100 AU, 115 AU. So on this scale, our whole solar system will fit into this box here. And this box is basically the size of the coronagraphic spot on Hubble, which it completely blocks, so it can see everything around it. And on this scale, the distance between the Sun and the Earth would be something like 1 projector pixel. So it's a very tough problem to solve, but the cool thing is that it looks like we can actually solve it. Technology does seem to be pretty close to being able to image these things. So before I get into how we image extrasolar Earths around other stars, or how we can image them, let me say let's take a look at what the image might look like, and what a planet orbiting another star, or an Earth-like planet orbiting another star would look like. We actually have images of our own Earth orbiting our Sun taken from outside the inner solar system. This is one of them, and you might think that this is an image of Saturn blocking the Sun, but I view it as an image of the inner solar system, coronagraphic image with Saturn acting as the external occulter, if you will. So one thing that you can see here is this little dot. Can people see that? That dot is the Earth. And this is a magnified image of that dot, and you may be able to see the moon there. So what I'm trying to show with this image is that the Earth-like planets are much, much dimmer than the star. Because the star, you see all sorts of lights from the star, but only 1 pixel is the actual Earth. Here's an image that was actually taken basically outside the solar system. And I was blown away when I saw this image first, because it basically shows an actual image, or mosaic, if you will, of our entire solar system. So it was taken by Voyager in 1990 as it was exiting the solar system. And what you can see here is the star, is our Sun right here. And on this square, you can't see Earth and Venus because they're too dim and too small. But if you process that image, then you can kind of see our Earth here, which would be located in the spot. And then you can also process all of these squares to find images of Venus, Jupiter, and Saturn, and everything else. So now, our own Earth is 10 to the 10, or 10 billion times dimmer than our Sun. So that is the brightness difference that we have to manage to be able to detect. Also, when Voyager took this image, the angle between the Earth and the Sun was something like 1 degree, if I remember correctly. But for the stars are so far away that even for the nearest star, Alpha Centauri, the distance between the star and an Earth-like planet in the habitable zone would be less than an arc second. It would be 0.8 arc seconds. And Alpha Centauri is the closest star, so the farther you go, the smaller that angle gets. So basically you have to be working at very small angles and with very high brightness differences. And we call brightness differences contrasts. So I'm going to use contrast to mean brightness difference. So just to kind of illustrate this point visually, this problem is similar to trying to detect a little firefly buzzing around a lighthouse from about 10 miles away. So this is right around the right brightness difference and the right angle. Okay, so enough of the fluffy stuff. Let me now move to how we can actually do this and the technology that might be able to let us accomplish this. So the main engineering challenge, I'm mainly an instrumentalist, so to me the main challenge can be described in terms of engineering specifications, and the two main specifications are 10 to the 10 contrast, which means the instrument on the telescope has to be able to image things that are 10 to the 10 times dimmer than the star, and also at an inner working angle of 100 milliarcseconds, or 0.1 arcsecond. Remember, Alpha Centauri is 800 milliarcseconds, but further away stars are the angle is smaller. And so 100 milliarcseconds means that we have to be working right at the diffraction limit of any reasonably sized telescope, such as 1 or 2 meters. And so the specification that we adopted is 2 lambda over d, which 2 times the diffraction limit of the telescope. Lambda over d corresponds to the resolution or diffraction limit of the telescope, where d is the size of the telescope and lambda is the wavelength. So what are the main obstacles to achieving these specs? I think the best way to show you what the main obstacles are is to look at why Hubble can't. So can the Hubble do this? And the answer, as I showed before, is the Hubble can't image Earth. So why can't it do it? Well, let's look at some random Hubble image, and let's zoom in on one of its stars. So let's consider, I don't know, pick this star, for example. So let's zoom in on that one. And this is what that star would look like if you had an ideal, fully resolved image of it with a magical telescope. In reality, what you would see is something like this. And this is the image of that star on the brightness scale, bright enough for you to be able to see Earths. So as you can see on that brightness scale, everything is completely washed away by diffraction and glare from that star, and you cannot see any planets because they're all obliterated by this light from the star. If you were able to magically remove the star, then this is what you would see. And so this is all with roughly a Hubble-sized telescope. And can people see multiple dots there? I keep asking this question. Okay, good. So now, one thing to point out is that with any reasonably sized telescope, such as the Hubble, we will not be able to actually resolve planets. Planets will be blobs, and the size of those blobs on the image would be much larger than the size of the planet itself. So on this scale, every planet will be much smaller than a pixel, but the image of that planet is larger than a pixel. So unfortunately, we would just be able to see one spot corresponding to a planet. However, we would be able to spectrally analyze that spot, and that's very interesting, and do lots of other things. But even before we're able to do that, we have to deal with the star. And the main problem with that star is these rings around it, which we call diffraction rings. And the reason that they're there have to do with diffraction. So when light enters the telescope, it goes through sharp edges of the telescope, and since light is a wave, whenever a wave goes through a sharp edge or encounters a sharp disturbance, it ripples. So basically, ultimately, the reason that images of stars in any telescope have these diffraction rings around them have to do with the fact that light, when it enters a telescope, it encounters sharp edges on the opening of the telescope. And this could be seen with water waves. So, when you have a current going through a little opening here, then you would see ripples going around there. And the same thing basically happens with light waves. So the main problem to solve here is to control the light from the star that goes where it's not supposed to be due to diffraction. There's many ways to eliminate diffraction from the star and the star itself. And the class of instruments that do this is coronagraphs. There are other instruments that can do similar things, like interferometers can eliminate the star, and there are also external occultures which can be used to block the star from far away. But what I'm working on in particular is coronagraphs. So I will, from now on, I'll talk about coronagraphs. Now, there are many different types of coronagraphs that have been designed to solve this problem, and they're all kind of related to each other and can actually be plotted on this tree of coronagraphs. But my favorite solution to this is to soften the edges of the telescope pupil. So the coronagraphs that work by softening the edges of the telescope pupil are called the apodization coronagraphs, because you're basically apodizing the telescope pupil. And so the way that this works is as follows. Basically, if you consider the telescope a simplified diagram of any telescope, you can reduce it to a pupil plane of a telescope and an image plane where you put your CCD. And actually, any instrument can be described like this. Your eye, camera, they all have a pupil plane and an image plane. Now, the relationship between the pupil plane and the image plane, for those who are mathematically minded, is the Fourier transform. And if you take the Fourier transform of a telescope pupil, you get rings, basically. And so, from the physics point of view, these rings can be thought of as being due to light entering a sharp edge here. And from a mathematical point of view, you get rings because the Fourier transform of this happens to be this particular shape. So now, if you know anything about signal processing, you know that to get rid of rings, you need to soften the edges. And this in signal processing lingo, this is called windowing. So if you soften the edges like this, then your image of a star, then all of the rings around your image of the star disappear, and you can now start seeing planets around there. And I'm going to ask this one more time. Can people actually see planets there, or are they too dim? Okay. Well, just trust me that there are now some planets there that you can see. Again, apologies for the bright room. So there's many types of pupil apodization masks that I've me and my colleagues designed and that I've worked with. Here are some of them. They're kind of interesting shapes, almost bordering on art, if you will. But the problem with placing a mask on your telescope is that it blocks photons. And we really don't want to lose any photons from Earth-like planets, because remember, a planet is 10 billion times dimmer than the star, and that's 25 stellar magnitudes, which places the magnitude of these planets somewhere around 30th magnitude. Now, 30th magnitude is about the brightness of the dimmest galaxies in the Hubble ultra-deep field, or deep field. So the number of photons we get is something like 1 photon per minute per meter square of aperture of our telescope. So basically, we don't want to waste photons. And there's a trick to apodize your telescope pupil without wasting photons. And you can do this by, instead of using masks, using mirrors. You can make two specially made spheric mirrors, and which concentrates. So if you look at the first mirror, it's illuminated by the telescope, by uniform illumination of the telescope pupil. And this, if you design the center of the mirror to concentrate light, but the edges of the mirror to disperse the light, then the illumination on the second mirror, you can design the illumination on the second mirror to be any shape you want, including your special apodization shape. And then you can use a second mirror to recollimate the beam, and lo and behold, at the output, you can get any shape that you want. You're basically reconstruct your pupil into any shape you want. So, and then when you bring this reconstructed pupil to focus on your CCD, then you would no longer get these diffraction rings on your star, and you can start seeing planets. So this is essentially the basic idea behind the concept that I'm working on. And this concept is called phase-induced amplitude apodization, or PIA, the PIA chronograph. So let me now describe more about what we do at NASA Ames. We have, I'm the technical lead for the Ames Coronagraph experiment, or we call it ACE, and it essentially consists of, the goal is to demonstrate this PIA technology to a level where we can see Earth-like planets. And this is a picture of what our lab looks like. Our experiment sits in this enclosure. It's a thermally stabilized enclosure. And we're also in a partnership with the high contrast imaging testbed in JPL, which is a vacuum testbed. And the dynamic between us and JPL is that we're a kind of a cheaper but faster testbed that advances the technology through low TRL levels up to about TRL 4 before vacuum demonstrations. And once the technology is ready to be tested in vacuum, we ship it to JPL, and it's tested there. So this is the experimental layout in our testbed. It's very simple. It's designed to basically simulate imaging of a star and then trying to get rid of that star so we can see how dark we can get the area around it and if we can see planets there or not. So we're creating our artificial star with a single mode fiber coupled laser. It's just basically effectively a geometrical dot out there. And then we are passing it through our PIA chronograph system. And so this here, we're pretending like this light has been delivered from our telescope, and then it's passing through our PIA system. And then we're focusing it essentially on the CCD. It passes through a few things. You can see our PIA optics here. There are two lenses, although right now we're switching to mirrors. And you may be able to see a uniformly illuminated laser beam right here being apodized into a tapered high contrast beam after the PIA system. Here are some initial images from our lab. These are a couple of years old now, but just to demonstrate the initial operation, this is an image that we get from our system without any chronograph, so just your old Airy pattern. When we insert our PIA system, we get an image like this, where there are no more rings. There's some artifacts, but there are no diffraction rings. And this is a simulation from our model. You can see there's a good match, except for some of this stuff there. So now, where the brightness of these things around this image is about 10 to the 4. So it's much, much brighter than an Earth-like planet is. So where is all that stuff coming from? And the answer is optical aberrations. So in order to achieve 10 to the 10 contrast, your optics have to be perfect to about the lambda over the square root of 10 to the 10, just 10 to the 5, and that's essentially atomic precision. And if they're not perfect, if they have aberrations, and no manufacturing method exists to manufacture optics like this, then what happens to your nice theoretical image of a star? So notice this is an ideal lens. So now if I put some aberrations on that lens, you start seeing speckles or leakage from that star that completely overwhelms your planets and could masquerade as planets, actually. So, but the good thing is that even though we cannot manufacture optics to the required precision, we can manufacture deformable optics, deformable mirrors, that we can then set to the required precision. And that's exactly what we're doing. We're introducing a deformable mirror in our optical train, and then using algorithms to counteract the optical aberrations and all the other optics in our optical train. So here's a picture of what our mirror looks like. It's a package about 4 centimeters in size. The actual mirror is 1 centimeter in size, and it has 1,024 actuators arranged in a 32 by 32 grid, so we can essentially put any 32 by 32 pixel shape on that mirror, including some interesting shapes here, and to try and remove all of these aberrations. In addition to that, we also need to stabilize the temperature of our testbed, and we actually have an active thermal control system with where we control the temperature of water running through the walls of our enclosure. If we don't do that, then temperature variations will misalign our system very slightly, and that would also create light leakage and from the star to go to where it's not supposed to, and to overwhelm our planets. So with our thermal control system, we're achieving about 1 millikelvin stability in our enclosure. 1/1000th of 1 degree Kelvin, or about 1/500th of degree Fahrenheit. And with that stability, we should be able to get to at least a few times 10 to the minus 9 contrast. So here are some lab results. The image that you see here is one of our latest images taken from our testbed. What you see here is an image of a blocked star. The star is here, and it's blocked by this razor edge that we put after our PIA system. And all of this light is light that leaks from the star due to optical aberrations. However, inside this area here, we have removed all of this light using our deformable mirror. And the average contrast in this region is 5.4 times 10 to the minus 8. And the inner working angle here is exactly 2 lambda over d, which is what we need to meet. So the contrast is not quite 10 to the 10. Actually, we arguably only need to get to 10 to the 9, because then you can use tricks to get to 10 to the 10 using software processing techniques. But we're getting close to achieving that, and this result has actually been a world record contrast for any coronagraph at 2 lambda over d up until a few weeks ago, when our partners at JPL have, with a similar system that they're now testing in vacuum, have gotten slightly better results. So we're happy about those results as well. And so just as a kind of summary of contrast levels, the star is at 10 to the 0, and Earth-like planets are at 10 to the minus 10. But if you get to 10 to the minus 9, suppression of stellar leakage, you may start being able to see those planets. And the current contrast with an inner working angle of 2 lambda over d that anyone has ever achieved, as far as I know, is somewhere around here. And JPL has recently reached a little bit of a better level there. And the contrast at 4 lambda over d is actually much better. It's been reached at the HCIT facility at JPL with a different type of coronagraph that's not as high performing, because it doesn't give you the resolution of 2 lambda over d. It only gives you 4 lambda over d. So we're basically marching down this road here, trying to get to better and better contrasts, and that's the goal of our testbed, is to demonstrate better and better contrasts. We're also, as I mentioned, manufacturing mirrors at Tinsley. The reason we want to use mirrors instead of lenses is because lenses are chromatic and they have ghosts. So ultimately, probably mirrors is the way to go, and not lenses. And here some images of what they look like. They're almost done. They should deliver them mid-September or thereabouts. And here are some members of our team and collaborators. So our team is maybe a half dozen people at Ames, but we're also collaborating with JPL, as I mentioned, Tinsley, and a few other folks. Okay, so now let me talk about the future and where all of this might go. So here are some possible missions that could use the PIA technology. My favorite mission is Pico, which stands for Pupil Mapping Exoplanet Chronographic Observer. And I'm going to ask this one more time. Actually, this image looks corrupted on my computer, probably because we switched computers. But in any case, this image I think everyone can see, and this is a simulated image using the Pico telescope of an Earth-like planet in the habitable zone around the star Tau Ceti. And the Pico telescope is designed to be 1.5 meters with the PIA chronograph. There are a few other designs using the PIA chronograph, such as the Wide Field Chronographic Telescope, which is going to be a flagship class telescope. It's 4 meters. There's another 1.5 meter telescope that may or may not use PIA. And there are also small kind of explorer-sized telescopes, so Exceed is a 0.5 meter telescope. This one is too small to detect Earths, but it might detect giant planets, and for sure will detect disks around other stars. You can also fly telescopes on balloons and have things be even cheaper, although maybe not as high-performing, and put these chronographs on them. On a small balloon telescope, however, again, you will not be able to see Earth-like planets, but you will be able to see larger planets and disks. I should also mention that in addition to chronographs and my chronograph, there are other concepts, such as the New Worlds Observer concept, which is just a standard telescope, but with a twist. It has a star shade flying tens of thousands of kilometers away from the telescope that blocks the star, but planet light can enter the telescope. And a few other things, a few other missions, that are also promising. So there's no shortage of missions. So once we have an image of an exo-Earth, what can we do with it? And this was supposed to be a nice simulated image of an Earth around Alpha Centauri with the Pico telescope. One cool thing that we can do is photometry. So as a planet rotates, if a planet has any features and it rotates, then we would be able to see diurnal or daily variations in the brightness of that planet. So we would be able to measure the length of a day on that planet. And also we would be able to, based on the shape of these variations, if the periodicity is not exact, we can infer some weather patterns on it. Although, as my wife once said, before looking at weather at other planets, I should learn to look at weather on this planet one day when I forgot to take an umbrella during a rainy day. So weather is, we can infer the presence of weather, but if the periodicity is not exact, we can also start, to get some hints about what planets are like. For example, if we consider this is a simulation of what a planet would, what a daily variation of the brightness of a planet would look like, based on whether our Earth is cloudless or having all land ice or having a lot of vegetation and so forth. Another thing, probably the coolest thing we can do, is spectroscopy. So this is a high-resolution spectrum of our own Earth, measured actually by looking at the Earth's shine from the moon. And you can fit various things to it, like oxygen, water, Rayleigh scattering, and a few other things, so you can start seeing all sorts of things. Of course, with a small telescope, we would not get a high-quality spectrum as this. We would only get a low-resolution spectrum. But even with a low-resolution spectrum, we can already start detecting oxygen and water, provided they're present in large abundances, such as they are on Earth. And of course, if we detect water and oxygen are biomarkers, at least on Earth, they're, of course, there because life is there. We would not have oxygen if there was no life. And also methane is another interesting biomarker. On Earth, methane is produced by life, so if we find large quantities of methane on another planet, then arguably also it's indicative of presence of life. So, and another interesting biomarker that we may be able to detect is something called the red edge. And if you look at the Earth spectrum, you might be able to see that this is a significant feature. It's a brightening of the reflection in infrared wavelengths. So this is called the red edge, and it's due to the vegetation on Earth. And the reason is that vegetation, so green plants on Earth, are not actually green. They're infrared, or I should say they're much more infrared than they are green. They reflect far more infrared light than they reflect green light. If you look at the reflectance of green plants, this, shown here, this peak is green, but right here is infrared. So if we had infrared eyes, we would not call plants green, we would call them infrared. But what this implies for Earth-like planet characterization is that if we have continents filled with forests, then lights reflected by these forests will have this red edge in the planet's spectrum. The reason, by the way, that plants are infrared is because infrared light is useless for photosynthesis and is actually bad for plants because it overheats them. So they reflect as much of it as possible. So presumably plants on other planets would also evolve to have a similar feature. So we would also expect to find large diversity of Earth-like planets. There have been some simulations, and people have been thinking up of many different types of planets. Carbon planets, that's basically a rock of diamond. And in our own solar system, no two planets are alike. So there's no reason to suspect that we would find planets that are like Earth or like Mars or like Venus among the next, dozens of Earth-like planets that we find. So all of this is very cool, but the problem is that budgets are a little tight, and in particular, if you can read that, we can only work with single-digit numbers. That's how tight our budgets are. And in order to make the best use of limited resources, the astrophysics community is organized to produce these decadal survey reports, which is a report produced every 10 years to prioritize missions for NASA and for other agencies. And this report is just about to come out, and a summary has come out. So I'm going to talk a little bit in the remaining couple of minutes that I have about the implications of this report for this kind of work. So now, I guess I should mention, for those who are not familiar with the report, this report is taken very seriously by Congress and by NASA and everyone. And typically, the next decade, the roadmap for the next decade is set by these reports, although it has not quite been true for the past decade, but hopefully it will be true this decade. So the main science objectives identified by this report, there are 3 of them, and one of the main objectives is called New Worlds, which is exactly looking for extrasolar planets. So this has been now officially identified as a third of what the astrophysics community should be doing according to the Decadal Survey Committee. So I'm very happy about that. However, they did not recommend any large or mid-scale missions dedicated to exoplanet imaging to fly next decade. And the reason for that is that they don't view the technology as being mature enough. So they are, however, saying that NASA should dedicate resources to technology development for exoplanet imaging. So in particular, the program that they recommend consists of 3 parts: large scale, mid scale, and small scale. And the large scale program has 4 priorities. The main one is what they call the Wide Field Infrared Survey Telescope, or WFIRST. And I'll talk a little bit about that in the next slide. Second one is Explorer program augmentation. An Explorer program is a program that launches small satellites, such as, for example, the EXCEED mission using the PIA chronograph that would be able to detect large planets, not Earths. But the one thing that's most relevant to exoplanet imaging is this part, which is part of what they call the mid-scale program. And the very first priority for the mid-scale program is the technology development for new worlds. And new worlds is imaging other planets, basically, and characterizing other planets. So the WFIRST telescope, which is essentially the flagship, proposed flagship telescope, for the next decade after JWST, consists of two parts. Probably the bulk of it would be dark energy, but also it would be able to do gravitational microlensing, which would get us exoplanet statistics. It would not be able to do spectroscopic characterization, but it would be able to tell us the distribution of planet masses. Now, the technology development program, as I said, this is the key, I think, to getting exoplanet imaging off the ground. So what they're proposing is basically for the next decade, we get the technology fully mature for exoplanet imaging and characterization, and then in the next decades, in preparation for a larger mid-sized mission in the following decade, meaning 2020 to 2030. So I think that's fairly positive. It could have been better, but I think it's still very good. And now thinking ahead, what can we do beyond that? Once we characterize the planet, the next step is to resolve the planet and to try to see features on the planet, or at least that seems to be the natural next step. And we might be able to do that with large baseline telescopic arrays. People have been thinking with such things, and one of them is called Planet Imager. So you may be able to resolve, to have a low-resolution actual image of resolved Earth, like shown there. And of course, even beyond that, we probably want to actually go there. So, one of my friends, Steve Kilston, proposed a bit of a tongue-in-cheek mission to be launched in 2500 AD. It would cost $20 trillion. Not sure if that's today's dollars or $2,500. And would take 1 million travelers. It would be a generation ship. So now, to conclude, let me, since this is a SETI audience, let me talk about some implications of finding another pale blue dot. So I think there are mainly three kind of different implications. First of all, of course, finding life. Finding life, we would answer a long-standing, profound 2,000-year-old question, of course. So that kind of speaks for itself. A new understanding of life and origins of life. Of course, there will be religious implications. Then also, we would provide targets for SETI. So even if we don't find, we find biomarkers, but not necessarily, well, definitely not intelligent life with these kinds of methods. But we would provide targets that SETI can then go and try to look for intelligent life on these planets, or maybe beam transmissions to those planets in hopes that someone there will hear them. And there's social implications. Provide a new exploration frontier, creating goals and meaning and reducing stagnation. History has shown that whenever a nation no longer has a frontier, an exploration frontier, they tend to decline and stagnate. So I think it's important to have that to make sure that Earth as a whole, if you will, doesn't stagnate. And also making science more exciting for the future generation. I think kids that I have to talk to are all about this stuff. You can't talk to kids about velocity distributions of galaxies, which might be fascinating to a physicist, but to inspire kids, this is the kind of stuff that inspires kids. So, making things exciting for kids may turn them away from maybe some bad directions and into more meaningful directions, such as science. And of course, another potential home for humanity, reducing risk of human extinction. This is probably not relevant today, but might be relevant hundreds of thousands of years from now. And changing perspective, like I said, Earth may not be a center of life. So, and that's, given how many Copernican revolutions there have been, I fully expect that this would also be a Copernican revolution, that Earth is not, it's too anthropocentric to think that Earth is the center of life, I believe. And a few other kind of philosophical things, making Earth squabbles seem more petty if we know there are other Earths, other life, and so on. So I'd like to finish with this. Let me go to my. So this isn't the Voyager image of Earth that I showed you a little while ago. The pale blue dot right there. And one reason that we're doing this is to really learn more about our Earth, because by looking at extrasolar Earths, it would tell us, not only whether life is possible to, can arise on other planets and therefore maybe give us a hint of how it arose on other Earth, but also give us a glimpse into the past and the future of the Earth, because presumably we would find Earths at various stages of evolution. And this is, I think, captured very well in this quote by T.S. Eliot, who says, "We shall not cease from exploration, and the end of all of our exploring will be to arrive where we started and to know the place for the first time." So, and with that, I'll conclude my talk. Sorry about running over and, well, starting late and running over. But thank you very much for your attention.
We'll open the floor for questions. Russ, can I start off with one?
Sure.
Is the coronagraph going to have applications in areas other than exoplanets? So, for example, can imagine gravitational lensing might
Yeah, there has been some discussion of that. So there are two parts to that question: whether the coronagraph itself can be used for other things, and whether the telescopic mission itself can be used for other things. So let me answer the second question first. So any chronographic telescope that flies, usually it can be used for general astrophysics because it's a telescope. It just happens to have a chronograph in it. There might be some design trade-offs because for a chronographic telescope, you don't need a wide field of view. You only need a narrow field of view. And so for general astrophysics, usually you need a wider field of view than for chronography, so that might add a little bit of the cost. But that's definitely a consideration in a lot of these missions, whether a chronographic telescope can be used for general astrophysics. Now to answer your first question, or I guess initial question, whether the chronograph itself, that is less likely, but still possible. So any astrophysical object which has a bright core that limits your detection of things around that core can be a target for a chronograph, such as, for example, galaxies with really bright cores. Arguably, you can also do things like look on the ground, which for surveillance and all that stuff. Although that doesn't grab me nearly as much as this stuff. But for example, if you have a bright searchlight,
or someone pointing a laser.
Yes, or someone pointing a laser. Yes, something like that. So, but much more fun to do this stuff, I think. So.
I wanted to ask first about the distance for your engineering parameters. Contrast to 10 to the 10th and about 100 milliarc seconds. That allows you to resolve an Earth-like planet in the habitable zone of a sun-like star. At what distance?
So for a sun-like star, we can go out to about 10 or I don't have this number off the top of my head, but it's on the order of 10 parsecs. So something like that. Well, we can do it this way. Alpha Centauri is, roughly 1 parsec or 1.3, whatever. and 800 milliarc seconds. So 100 milliarc seconds is 8 times the distance of Alpha Centauri. So that would actually be so that's about 10 parsecs.
That's
right.
dozens of stars.
Yes, that's dozens of stars. Although you also have to be careful because it depends on the type of the star. If a star is dimmer, then the habitable zone is closer in. If it's brighter, then it's farther out, and so on. So there's those parameters. And also, double stars can be problematic. Alpha Centauri is a double star, which poses a little bit of a challenge to us because we block one of the stars, but the second star is still there, and that's hard to block. So.
Thank you.
Hi. At SETICon, Frank Drake said that he had lately become interested in red dwarfs and their smaller zones of habitability as potential SETI targets.
Right.
And in sort of playing off your last answer, what do you think, is it a lot easier to detect a closer planet in a zone of habitability to a red dwarf, or is it harder? How does the math work out compared to a solar type star?
Sure. Unless we're very lucky, I think we would not be able to find Earth-like planets around red dwarfs with these methods. And the reason is that for red dwarfs, the habitable zone is just so close in that the angle is just too small. Unless we launch a large telescope, if we launch an 8-meter telescope, then I think we would be able to survey the nearest red and red dwarfs. So, but also, yeah.
So, fairly early in the talk, you showed a graph showing that over time there's a linear relationship between the size of the planet and the number discovered.
Right.
But the Earth-like planets discovered so far are extremely close to their stars, not in the habitable zone. So I wonder, what the expectation is in terms of how that graph would play out when you get out to the habitable zone.
Sure. Yeah, that's a very good question. And of course, that graph didn't show. Probably a better thing to have done was to show that graph for planets within habitable zones. Problem is that we would have very small number statistics there, and you would not be able to see any trend. I think there is some correlation between the size of a planet and the distance from the star. So, smaller planets might. I'm not sure how solid this correlation is, or how solid the statistics is with the discovered planets. But I think there's a hint of the correlation that smaller planets are more likely to be closer in, or at least if you exclude obvious things like hot Jupiters that migrated in. So the answer is that nobody knows, what the size distribution of planets is in the habitable zone right now, we can start waving our hands and extrapolating and saying that we don't see a strong correlation between size of the planet and distance from the star, and therefore the distribution of planet sizes that in that graph that I showed is also likely to hold for planets in the habitable zone. But we can't say that for sure yet, and we need to await more results from Kepler to answer that. And in particular, I should mention that the Kepler results that I showed are all for planets with very short period orbits, because all of the data is only for the first month or a couple of months or something like that, and so they've only observed planets who were only released planet candidates whose orbit is very short, and so they're very close to the sun. But I guess the main point is that I don't think there's any strong reason to believe that this would not hold for other distances from the star. Yep.
You say that your system is very hungry for photons.
Yes.
But if I understand correctly, or coronagraph is monochromatic. Do you see any hope for a broadband coronagraph?
Yeah, that's a very good question. So I didn't. So the demonstration that I showed during my talk was for monochromatic light. However, the coronagraph design, at least the mirror coronagraph design, not the lens one, is designed to work at a broadband or relatively broadband, and by that I mean it's designed to work in a 10% band, meaning the width of the band is 10% of the center wavelength. So what will probably happen is that we will have different spectral channels in our telescope. So, and each channel will maybe have a bandwidth of 10 or 20%, and then each channel will have its own coronagraph and wavefront control system. Or maybe we can think of a extra, wideband coronagraph design. There's been some work there as well that works in a wider band. So.
What is inflation technology development program that was mentioned on one of the slides? Is it related to balloon missions or what is it?
Sorry, what's related to?
Inflation technology development program.
Inflation?
Yeah.
That was part of the Decadal survey.
Oh, okay. Let's see. I am not sure about that. I've been reading the Decadal survey, summary with an eye for exoplanet stuff. So I don't. I'm not sure what the inflation is, but it might.
It was recent, yeah.
Right here?
Yeah.
Okay.
Next.
Yes. So the inflation technology development program. I don't know, but if you look up the Decadal survey, I think Google Astro 2010, then you'll be able to see some of these slides there. I just took these slides directly from their talk. So, yeah, sorry, I don't have a better answer for you.
Also, you mentioned one of possible options, balloon missions for this instrument. So how heavy this instrument has to be? How heavy?
I don't remember the weight, but we did a kind of detailed study and submitted a proposal. So it's it's a smallish telescope. It's 0.5. It's a 0.5 meter telescope. So I understand there's several levels of balloon load capacities. So this would not need the largest load capacity for the balloon. It would be I think one of the medium class balloons. So I think that's as the best I know. But if you're interested, I can look up the actual number on my computer, the actual weight. Come talk to me after that.
Okay, if there are no more questions, we have one more quick question.
I wanted to ask you a follow-up on the monochromatic issue.
Sure.
You talked about measuring spectra. That would seem to contradict with the idea of monochromaticity.
Yes. So I guess let me be a little bit more clear. So the test we're doing right now is in monochromatic. However, the ultimate telescope would work in broadband. So the idea is that we demonstrate things in monochromatic light first and weed out all the issues that are not related to broadband. And once we demonstrate high contrast in monochromatic light, then we switch over to broadband and continue our demonstrations in broadband light. So JPL has actually been doing some broadband demonstrations with other coronagraph designs that work at 4 lambda over d, not at 2 lambda over d, but 4 lambda over d. And they've demonstrated something like a few times 10 to the minus 9 contrast, or maybe even 10 to the 9 contrast, in a 10 or maybe even 20% band. I don't know I don't remember the exact numbers, but it's on the order of 10 or 20% band, and the contrast is something like 1 or 2 times 10 to the minus 9 at 4 either at 3 or 4 lambda over d, so roughly. And to see an appreciable number of Earths at 3 lambda RD might require a larger telescope. So that's why there's an incentive to go to 2 lambda RD, which is the primary goal of this coronagraph design.
Okay, if there's no further questions, then we join me in thanking Rus for his great.